This is a problem that will test the abilities we've just acquired. It's going to test our ability to find voltage, define electric field, potential energy, and force. So the first thing this problem asks us to solve is what is the voltage going to be at this point right here due to this 1.6 times 10 to the negative 19 Coulomb charge right here. So we're going to apply the voltage equation, and we're going to write it down first. Voltage equals K times Q over R, which we know is equal to 9 times 10 to the 9th, 1.6 times 10 to the negative 19 coulombs, over R of 0.5 times 10 to the negative 10. And we get an answer of 28.8 volts, or joules per coulomb. 9 times 10 to the 9 for K, it's a constant that you know. Q is the charge of the point right here that's causing the electric field. R is the distance from the electric field. Now the problem asks us to solve electric field. And before we go on to that, note that voltage is synonymous, or the same word, as electric potential. Electric potential and voltage mean the same thing. Now, we need to solve electric field. Electric field is equal to K times Q over R squared. We know this is equal to 9 times 10 to the 9th over the charge Q over R squared. 0.5 times 10 to the negative 10. And we square this. And we get an answer of 5.76 times 10 to the power of 11 newtons per coulomb. Now the problem asks us to solve for potential energy at this point. If this point's a proton, and we know that the charge of a proton is 1.6 times 10 to the negative 19 coulombs. We just solved for voltage, and we know that units of volts is the same thing as joules per coulomb. So let's solve it that way. Potential energy of a proton placed at this point is equal to the voltage at this point due to this charge that causes the electric field of 28.8. Instead of volts, I'm going to say joules per coulomb because the charges will cancel out. So joules per coulomb times the charge we're going to put right here. And that charge is the charge of the proton put right here of 1.6 times 10 to the negative 19 coulombs. We solve this out, and we get an answer for the potential energy right here of a proton of 4.6 times 10 to the negative 18 joules. Now, remember the tree example we did in the last video. And I told you that at ground, at the base of the tree, where the apple was going to fall to, the potential energy there was 0 joules because it's ground. Energy is always relative to something. This is relative to something too. The potential energy, when we're talking about electric fields, ground, or a potential energy of 0 joules, is always, or in almost every situation, infinitely far away from the point charge. But this makes sense, because look at this equation which describes potential energy per charge. If we're an infinite distance away from the charge causing electric field, R will be infinity, which means that voltage, or joules per coulomb, goes to 0, which means that our potential energy is 0. Also notice how I use units to solve this problem. I saw that I needed potential energy of units of joules, and I knew I had an answer. I knew I had a term that was joules per coulomb, and I had a term that was coulombs. And I saw that I could cancel the denominator with the numerator to get joules. This is an excellent way to solve problems if you're stumped. You don't know. Look at units, figure out what units you need for your answer, multiply terms you have in the problem together to get the units you want. And most likely, that answer is going to be one of the multiple choice answers, and you will get that problem right. Now, the second part of the problem asks us, if we have a proton at this point, what is the force on the proton going to be in magnitude, and what direction will it move? We know that the force equation is K times Q1, Q2 over the distance squared. This gives us 9 times 10 to the 9th times 1.6 times 10 to the 19th coulombs for this charge times 1.6 times 10 to the 19 coulombs for this charge over the distance between the two charges squared, which gives us an answer of 9.2 times 10 to the negative 8 newtons, which is the magnitude of the force. So like I said in the last video, use this equation, figure out what the magnitude of the force is, and then look at the signs of the charges, figure out if it's going to be attracted or it's going to be repelled. We know that both of these charges are positive, and they're going to move away from each other. So this one wants to move away from this one, so it's going to be pushed this way. So we know that the force is this force to the left, because it's repelled, because both have positive signs. Same sign. However, let's say that instead of solving this problem with a proton, this was an electron. We would have gotten a negative force here, so we would have actually moved towards it. You could do it this way, or you could say, I'm just going to do the magnitude. Forget sign. I get this magnitude. It's a negative, but forget the negative. I get this magnitude. And then I say, okay, different sign of charge, they're going to be attracted, so they move towards each other. So I would say to the right instead.